I've selected a set of elements to focus on some key features and key things you need to know about photoelectron spectroscopy. So as we're looking at our graph, across the x-axis, that corresponds to the difficulty to remove the electrons or the ionization energy. Sometimes it's shown as kinetic energy, delta U, binding energy, but it's really a measure of just how much energy was needed to remove an electron or a group of electrons. The y-axis is normally labeled properly as peak intensity, but it's related to the relative number of electrons with a certain ionization energy. So we're going to choose some to look at here for important patterns and for some descriptive ability that they have. So hydrogen is the simplest of all PES because it's the simplest of all atoms. The hydrogen atom has one proton, it has one electron. So when I shoot my X-rays at it, that electron leaves, and we can determine that it has an ionization energy of 1.31 megajoules per mole. So we've got a value and we've got a height. When I go to helium, there's two key differences. The value is slightly higher, and you may notice that the axis is numbered backwards here. That's because our electron analyzer is technically measuring the speed of the electrons. So the higher the ionization energy, the lower the speed of the electrons. So that's why these are almost always numbered backwards. And they're also very often shown as a log scale. So it's important to look at the labels on your axis as well. But right there, it has two differences. One, the value is larger, and second, the peak is taller. The peak is taller, we have more peak intensity because our detector is detecting twice as many electrons. We aren't knocking off two electrons at once. We are, because I have helium that has twice as many electrons, I have twice the chance of knocking off an electron and twice the chance of detecting it. So I have a peak that is twice as tall. That indicates that I have a place in my atom with two electrons. The value in terms of ionization energy is also higher. It's 2.37 instead of 1.3. That value is higher because I have more protons in my nucleus. There's two protons holding onto the electrons, so they are not exactly twice, but almost twice as hard to remove. When I go down to some more samples here, I see additional peaks. Because we've already seen electron configurations, we should understand that electrons aren't all in one place, but are broken down into smaller sections of levels and even down into sublevels and orbitals. Beryllium has two peaks. It has some of its electrons in a place that requires 11 megajoules of energy, and some of its electrons in a place that requires slightly less than one. That means some electrons are close to the nucleus and some are farther away. It doesn't clearly have the labels and the lines showing 1, 2, 3, 4, 5, 6, 7, 8 electrons here, and that's intentional. Sometimes it will, sometimes it won't. But what we can notice is there's an equal number of electrons in close to the nucleus as are farther away. And because we know this is beryllium and there's 4 electrons, this corresponds to the 2 electrons in level 1 and the 2 electrons it has in level 2. Boron is next. Boron has a higher value here and a higher value here. The higher value in this case corresponds to a greater number of protons. The close electrons, rather than being attracted by 4 protons, are attracted by 5 protons. So we have a greater amount of energy needed to remove them. Here we have some that require a little bit more energy than these did. But I have a shorter peak that requires less energy. So the high amounts of energy mean that they must be close to the nucleus. The lower amounts of energy within a spectrum mean they must be further. So what I'm seeing here in boron is some electrons close to the nucleus, some further away, and some slightly further away. This is one of the pieces of data that really supports well some trends in ionization energy that we'll talk about, and the idea of sublevels within a level. Both of these are peaks correspond to electrons that are farther from the nucleus than this, but there's a subtle difference. When I look at these compared to these, it's over 10 times more energy. These are significantly harder to remove than 19s. The 1.3s are way easier, and the 0.8s are slightly easier. So this lines up with what we know about boron. There's 2 electrons in the first energy level, and then in the second, I use the 2s and the 2p sublevel, and there's 2 here and just 1 there. So the height is also giving me relative number of electrons. So as I compare one to another, a difference in value for the peaks is based upon this has a certain number of protons, this is different. And when I'm within a spectrum, I'm talking about different distances from my nucleus. Neon is down here. Neon is still at the end of energy level 2. We see a huge ionization energy there relative to the 1 to 11 or 19. It takes 84 megajoules, so way, way more energy. And then I have a 4.6 and a 2.8. So this is about 20 times higher. This is just over 2 times higher. Each separate bar or peak is a sublevel, and the peaks that are close to one another are sublevels within the same level. And when we connect this with neon, which we've seen has an electron configuration of 1s2, 2s2, 2p6. Going on to calcium, obviously skipping a whole bunch in between, we can see our pattern continue to emerge. There are several sublevels that max out at a height of 2 or at the same height as one another. There are a few sublevels that max out 3 times taller. This is evidence, or this is support of the fact that I have S sublevels with 2 electrons, P sublevels with 6. If we had a spectrum that involves the D, we would see an even taller peak when that becomes full. But I have groups which are close to one another. I have ones by themselves. So I'm talking about levels and sublevels within the same level. And then here, it's important to note that even though calcium has 20 protons, those valence electrons have a very, very low ionization energy, the lowest we've seen so far, in fact, because with calcium, I fill level 1, the 2s, the 2p, the 3s, the 3p. Those electrons are all the way out at the distance that corresponds to the 4s. So even though we have more protons, that distance is an important factor as well. So there's some great questions here, but if you just want to see the graphs for all these different elements and see if you can understand the patterns, the graphs themselves are right there for you as well.